Hi, in order to complete the study of hydraulic pumps that my colleagues have developed, we are going to talk about positive displacement pumps in depth. Positive displacement (PD) pumps are not well understood by most users and specifies. Properly applied, PD pumps offer significant opportunities to improve processes, improve efficiencies, and reduce costs. PD pumps come in many designs and operating ranges, but they all work on the same principle. An increasing volume is opened to suction, filled, closed, moved to discharge, and displaced. The delivered capacity is nearly constant throughout the discharge pressure range. This constant capacity will intersect a system curve at a defined point, allowing a high degree of system control. The positive displacement pumps can be divided into two main classes: reciprocating and rotary. Typical rotary pumps are gear pump, vane pump, screw pump, progressing cavity pump, low-bore cam pump, and peristaltic. On the other hand, typical reciprocating pumps are piston pump, plunger pump, and diaphragm pump. The positive displacement pump is in some ways an even simpler device to control than the centrifugal pump discussed previously. It has the same function, namely to provide the pressure necessary to move a liquid at the desired rate from point A to point B of the process. The figure shows a generic process with a positive displacement pump connected to deliver liquid from A to B, in this case a gear pump. Their characteristic curve is so simple that it is rarely drawn. The point at which the system curve and the pump performance curve intersect is the condition of operation. Typically, a system curve will require higher pressures for higher flow rates. Centrifugal pump performance has reduced flow with increased pressure. The slopes of the two curves are opposite. If the slopes are both gradual, the angle of intersection will be small. Minor variations of resistance to flow, partially clogged strainer, valves, etc. will shift the point of intersection over a range of operation. PD pumps have a nearly vertical performance curve and, therefore, always intersect the system curve at one point. Minor variations in system resistance do not alter the flow. Rotary pumps are defined as being vane, piston, flexible member, lobe, gear circumferential piston, or screw pumps. In all of the rotary designs, the chamber is created progressively through rotation of the drive shaft. There may be one or more chambers opened per revolution depending on the design. The chambers are sealed off from suction by close clearance between the rotor and the housing, or by close clearance between intermeshing rotors. Rotation of the shaft moves the chamber along the bore or housing towards discharge. The chamber is displaced to discharge by rotation. The release to discharge progresses with rotation, as the volume is expelled so that the flow is typically pulsation-free. Reciprocating pumps are defined as being steam, power, or controlled volume pumps. In all reciprocating pumps, there are check valves on the suction and discharge. Fluid flows through the suction valve and into the chamber as the plunger, piston, or diaphragm recedes. At the end of the stroke, the chamber is at its maximum size. The suction valve closes, the plunger moves forward into the chamber, forcing the fluid out the discharge valve. The flow from each chamber is a pulse flow. If the pump has several chambers, they are timed to have sequential pulses, to minimize the overall pulsation. As the gears rotate, they separate on the intake side of the pump, creating a void and suction, which is filled by fluid. The fluid is carried by the gears to the discharge side of the pump, where the meshing of the gears displaces the fluid. The mechanical clearances are small, in the order of 10 micrometers. The tight clearances, along with the speed of rotation, effectively prevent the fluid from leaking backwards. The rigid design of the gears and houses allow for very high pressures and the ability to pump highly viscous fluids. Lobe pumps are similar to external gear pumps in operation in that fluid flows around the interior of the casing. Unlike external gear pumps, however, the lobes do not make contact. Lobe contact is prevented by external timing gears located in the gearbox. Pump shaft support bearings are located in the gearbox, and since the bearings are out of the pump liquid, pressure is limited by bearing location and shaft deflection. 1. As the lobes come out of mesh, they create expanding volume on the inlet side of the pump. Liquid flows into the cavity and is trapped by the lobes as they rotate. 2. Liquid travels around the interior of the casing in the pockets between the lobes and the casing. It does not pass between the lobes. 3. Finally, the meshing of the lobes forces liquid through the outlet port under pressure. A screw pump is a positive displacement pump that uses one or several screws to move fluids or solids along the screw S-axis. In its simplest form, the Archimedes screw pump, a single screw rotates in a cylindrical cavity, thereby moving the material along the screw spindle. This ancient construction is still used in many low-tech applications, such as irrigation systems and in agricultural machinery, for transporting grain and other solids. The simplest vane pump is a circular rotor rotating inside of a larger circular cavity. The centers of these two circles are offset, causing eccentricity. Vanes are allowed to slide into and out of the rotor and seal on all edges, creating vane chambers that do the pumping work. On the intake side of the pump, the vane chambers are increasing in volume. These increasing volume vane chambers are filled with fluid forced in by the inlet pressure. Inlet pressure is actually the pressure from the system being pumped, often just the atmosphere. On the discharge side of the pump, the vane chambers are decreasing in volume, forcing fluid out of the pump. The action of the vane drives out the same volume of fluid with each rotation. Multi-stage rotary vane vacuum pumps can attain pressures as low as 0.1 pascal. The fluid is contained within a flexible hose or tube fitted inside the pump casing. The actual pumping principle, called peristalsis, is based on alternating compression and relaxation of the hose or tube, drawing content in and propelling product away from the pump. This process makes a peristaltic pump an accurate dosing pump or metering pump, with an equal amount of liquid dosed each time. The liquid being pumped never comes into contact with any moving parts, because it is totally contained within the reinforced hose or tube. A rotating shoe or roller passes along the length of the hose or tube, creating a total seal between the suction and discharge sides of the pump. As the pump's rotor turns, the sealing pressure moves along the tube or hose, forcing product to move away from the pump and into the discharge line. Where the pressure has been released, the hose or tube recovers, creating a vacuum, which draws the product into the suction side of the pump, the priming mechanism. Combining these suction and discharge actions results in a self-priming positive displacement pump, the peristaltic pump. An axial piston pump has a number of pistons, usually an odd number, arranged in a circular array within a housing, which is commonly referred to as a cylinder block, rotor or barrel. This cylinder block is driven to rotate about its axis of symmetry by an integral shaft that is, more or less, aligned with the pumping pistons, usually parallel but not necessarily. A diaphragm pump or pneumatic diaphragm pump uses a combination of the reciprocating action of a rubber, thermoplastic or Teflon diaphragm and suitable valves either side of the diaphragm to pump a fluid. When the volume of a chamber of either type of pump is increased, the diaphragm moving up, the pressure decreases, and fluid is drawn into the chamber. When the chamber pressure later increases from decreased volume, the diaphragm moving down, the fluid previously drawn in is forced out. Finally, the diaphragm moving up once again draws fluid into the chamber, completing the cycle. This action is similar to that of the cylinder in an internal combustion engine.